All right. It should be recording. Yes, it is. So welcome everybody. So this time I'm going to continue the last stream and I'm going to implement a interpreter for the language we passed last time. So let me share my screen. And you can see the screen, right? Should be good. And so last time we implemented this parser that could parse a simple functional language like this. And what we want to do today is we want to take the AST that we passed, which we have here in E, and we want to interpret it into a value. So let's just get started. And let me know if there is anything wrong with the stream or whatever. So an interpreter takes an environment and it takes an expression and it gives a value, right? So if we remember, P expression is these constructs and values are these guys. So let's do the imports. And I guess we need a tree as well. And the interpreter is pretty simple in the sense that we just switch on all the different constructs in the AST. So the compiler is helpful. It will show me the cases I haven't done, and it will do it in a way where I can easily copy and paste all of them. Now I happen to know that all values, they evaluate to themselves. So I can just do all of those in one go like that. And then I'll just copy and paste the rest and start to implement them. ID is simple. That's going to be lookup tree. And for now, I'm just going to say if there is a mistake, we'll just make the value error. That's going to be a simple way to do it. So let binding. OK, so we got to evaluate the value. So we interpret that one. In the environment, the value. And then we have to make a new environment where we set the ID to that value, and then we evaluate the body in this environment. All right. So a condition, in the if statement, we evaluate the condition. And I forget, did we have bools or not? Yes, we did have bools. So let's say that. OK, so what we want to do, depending on the result, if the condition is P bool true, then we want to evaluate then. Otherwise, we're going to evaluate else, right? So a call, we got to evaluate the function. And that has to be a lambda. Otherwise, we cannot call it. Whoops. So if it's a lambda, what I'm going to do is I'm just going to say to do now. And we'll get back to that in a minute because I want to check what I've done so far so I don't have too many mistakes. And if it's not a lambda, it's a mistake. Lambda, okay, this one is a little tricky. We'll get back to it in a minute. For now, we'll just return itself. An array, was this an array value or just an, no, it's an, it's this one. So this one becomes array values and we map each of them and interpret each of them. Like that. And the sequence, what you do is that what should the result be if it's the empty sequence? What do you think? We don't have a void value. We could add that, or we'll just say it's going to be true. It's just to demonstrate. like that. Okay, so I made some mistakes. Let's fix all of those. Missing a bracket. Args is redefined. Yeah, lambda args here. Return from the switch. So what does it say here? One of the cases doesn't return a value. What was value? Yeah, we have a case that returns a lambda. So the simple thing to do is just to add it as a value. That should do. All right. So now we have an initial first version of it. Of course, it's not complete, but let's just call it and see. We give it the empty environment at first, and then we evaluate it, and then we print the value. So we got to import it first. Like this. Okay, so if we run that, we get the to-do implement value and then another to-do. Okay, good. And the other to-do was a call. So maybe let's just do call. So what happens in the call is that we have some arguments. We got to evaluate the arguments. Map, that's the same as array. We have that code down here. Let's just copy paste it for now. So now we have all the arguments, okay? And then we gotta bind the arguments in the lambdas to these, but we have to check that the number of arguments matches. If they do, then we can do something. Otherwise, it is indeed an error. We'll choose that, do that for now. Okay, so if they are the same, then what we do is that we build up a new environment by binding the names of the lambdas to the values we get. So this is a string, just so we can clarify that. And then we're going to say set tree ACC larg, and then we're going to say eargs I. Right, so using fold I is a helpful pattern in these cases. We know these two arrays are the same length. So by using fold I, we can easily, you know, in other languages, it's a common pattern to zip them, but I like this one just because. And then we have the new environment, and what we do is we evaluate the body of the lambda in that environment. Okay, so now we might even have we have something that's wrong. It says error. Okay, so where does that error come from? So we have too many errors. Unknown ID. This one should be instead. Let's try that. And this error is expected lambda. Okay, is that it? Let's try that. Let's see what happens now. Okay, interpret, I got something wrong. What did I do wrong? Oh, the parentheses here. Expected lambda. So what did I do wrong? Let's just print what it is instead, and maybe we can get a hint from that. As you've seen many times, I'll just use a print to figure out what's going on. All right, a new hint. Now it's because we're calling these IDs that didn't exist. Okay, so it's because the program uses less than, multiplications, minus, and so on. And the way the grammar works, it'll just interpret those as calls. So if we look at how we did it, when we passed it, and we will just turn those guys into calls with the these operators we had. I forget where they are. They are somewhere. I guess in here. Yeah, down here we have these different operators that we define for the different built-in operators, and each of those guys are converted into a call. Okay, so what we need to do is that we need to probably extend our environment with built-ins, or we can just put it inside the interpreter. So we'll just say, when we look up a name here, we're going to change it to just look up the name, and maybe it has a value, and if it has a value, return that. Otherwise, we'll say interpret built-in. Okay, so we'll just assume it's a built-in and implement this guy. Okay, so it takes an ID and it's gonna give us a value. And okay, so here I'm gonna say, let's do, for now we'll do it inefficiently, but we can improve this in a minute. So we have this guy here. Let me just show the structure of it. So the fn to implement this guy, I'm gonna pass to tree. I'm gonna build a tree of IDs, and inside that tree, I'm gonna have a function that, no, it can just be a lambda, right? No, the problem is it has to be implemented, right? I cannot return a lambda because it has to do the real code. So this is in fact wrong. I have to do it here. So we have to check if fn is a built-in variable before we evaluate it, because we have to evaluate it with code. So that's another way to do it. Okay, so let's just change this. P string, unknown ID. Let's return it back to what it was. And then here we're going to say handle built-in. So we're going to evaluate the arguments because we need those always. And then we're going to say handle built-in EA. And maybe it's handled, maybe it has a value, built-in call, like that. And if that gives a value, we're gonna keep that. Otherwise, we're gonna fall back to this thing. So that's gonna be the idea. Okay. So this function is this one I started here. It takes an ID and it takes some arguments that are p values, and it returns maybe a value. If we can handle it, we'll return it. If not, we'll just return none. Okay. So let's just see if I did this right.
So you just look up tree. That's it. Why do you need this at the end? I mean, return none.
Because I have to implement something here.
Okay.
But it's not a string. We get a p expression here, right? So these guys, well, this is a roundabout way to do it, but okay, it'll do for now. Let's just test it. And then we get a function which is supposed to compare these guys, okay? And then return it as an int. So to do that, the best way is to say, let's do a compare two values, left p value and right p value, and then return. It's like the spaceship operator. It returns 0 if equal, -1 if left is less than right, something like that. I believe that's the convention. Okay. So let's do it like that. We'll just we have all the different kinds of values here. If it's a bool, we expect the right side to also be a bool. So there's a left bool and a right bool. So this is a little bit so we have b to I l. Do we have? No, we don't have the space. So, okay, what should it be? There are like, this is too complicated. What is the proper comparison? Oh, I can probably just do comparison in flow. It might have it defined. No, I can't, because I have to. Okay, if they're the same, then it's 0. Else, if Let's just do it like that. If this one is less than that one, then it's -1, else it's 1. Okay, that'll work. So this is, maybe I should say it's -2, so I have a chance to debug it if it's wrong. For now, well, we'll do the similar thing for the other guys, and let's just format this a little bit nicer. I'm thinking we have some functions in here, right? Get strings, yes, I remember that. So we can do it like this. So we can say get in similar to these guys, so we don't have to do the nested switching. That's a little bit nicer. We'll just get some helpers here that will return integers. If it's an integer, just say 0 if it's not, and so on for the other types. That'll clean up the code a little bit. Of course, this won't give any errors if you really wanted to. So what we're going to do is that we're just going to say, okay, if this is a bool, then the right bool is going to be get bool from the right. We don't need the switch. And then we have that guy. And in fact, now that I look at this, isn't this exactly generic compare that we have in algorithms? I think it is. Generic compare. There you go. That's exactly what it is. So let's use this guy. LBR. Okay, and let's import that. Is it in DS? I don't remember. No, it's just directly. Okay. So that cleans it up. Now we can do a one-liner. And lo and behold, it's going to be easy to do these guys as well. This one is a little more complicated, and this one is a little more complicated. For now, we'll say, you know what? We'll just use generic compare. Maybe that would work for all of them. Would that work for all of them? That's very interesting. Maybe it would. Probably compare p-value is just this function. Sometimes it's simpler than you make it. All right, let's just clean this up and get this implemented up here. So we have less than here, and what we want to do is that the result is the comparison between arg0 and arg1. How is it? So this will return -1 if it's less than. Or, okay, so if it's less than or equal to 0, okay? And it's not an int, it's a bool. Is that correct? I believe it is correct. No, we don't want to give it arguments like that, and it has to be some. Get p int is not exported. Incompatible types. Yep, indeed. Okay, so let's see if we can at least make some progress. Unknown ID minus. All right, let's do minus. So I know I could add all the other comparison operators, but I just want to get this up and running. So this one will be subtract p-value. Let's just do it like that and make a function that does that. Okay, and once again, we'll switch. Well, okay, we only want to do subtraction on integers, so we'll just do it like this. P int. So get p int right minus get p int left. Isn't that right? I believe it is. Like that. And this guy wanted 2 arguments. Okay, I see. So maybe it's not worth it. Maybe we'll just inline it after all. Maybe we'll just inline it after all, since it's so simple. It's 1 here, and then it's 2 here, like that. Correct? And then what else does my program use? We'll just do what we need. Multiplication is the last thing, I think. So let's add multiplication. Okay. Minus 20. So something's wrong. Did I swap these guys? I guess I swapped them. Yeah, I shouldn't do it. They already come in the right order, the way the parser does it. So we shouldn't swap these guys. 120, is that correct? Factorial of 5, is that 120? Does it have factorial, this guy?
Yeah,
Yes.
it's right.
Oh my God. All right, so we have enough that the basics work, but obviously we know we don't have everything. Okay, so remember, we have this guy where we have all the different names. So what I'll do is just grab all of them to make sure we implement all of them. Call lambda. Okay, we have these guys, and I guess that's it. Okay. So let's implement the other. Okay, I can put these on one line. Okay, so we'll do plus. Okay, plus could be defined for strings, but that requires overloading. I don't know. I know Flow does that, but in this language, maybe I don't want to do overloading. Maybe I want to have another operator. Oh, now I removed multiplication. That was a mistake, but like that. And then we have modulo as well, right? So that's those 5, and then all the different comparisons. So then we just change it to like this. Equals, that's equals to 0, and bigger than, that's like this. It's very symmetric. This spaceship operator is a nice one. All right, so that's all of those guys. And it's just not as easy. It's similar.
Probably you missed not equal.
Okay, thanks. Not is like that, right? And negate is like that. And then these two guys, let's do not equals as well. Okie dokie. And then the binary operators for bools. Let's do those guys. And so that's like, maybe it's in fact a comparison, but anyways, get p bool arg0, and these guys are not too hard to implement. It's just a lot of copy and paste. And it's always here when you do this copy paste, you have somewhere you have a 0 instead of a 1, and then you spend 10 hours debugging why it doesn't work. So therefore I should technically test all of these guys, but you know what, I don't want to. Now, I know this interpreter has a problem. I think the basics work now, but here we have this guy. So does anyone know what the problem is here? Why isn't this correct to just return the lambda as is? I'll show you. So let's do a program here. Let's just test this one, right? That should work. And and it gives us 3. Okay, so what if I do 1 like that and I say add 1? That also works, but if I make a function inside, basically the point is closures, they don't work. If I have recursion and closures, what program can I do to demonstrate it? Come on, we have to have some good idea here. Maybe we'll just
try to return the same, but just call it 1 again. Maybe this way. Add 1 inside of add 1. I mean.
No. What I'll do is that I'll say make adder, and it takes the number and it returns a function that's that number, like this, right? So add 1 will be this guy on 1, and add 2 will be this guy. Okay.
Mm-hmm.
I think. Let's try that. Maybe I'm wrong. So this should be 3 if we're right. Are we right? I think we're right. I got a parsing error. I need a semicolon here. What am I doing wrong? Can anyone see what the problem is? Maybe there's a bug in the grammar. Oh, I didn't have syntax lambda here. Okay, args. Expression. And okay, it's because it's a sequence, but we don't support sequences at the top level, right? So a semicolon requires either let binding or semis. So we have to use these guys to get a sequence. So in this language, you don't have sequence at the top level. So we'll just do like that. That should help. And now we got a little bit further. So here, this semicolon is wrong. This language is very tricky about semicolons. And now you can see it gave 0, so it doesn't work. It doesn't work. And the reason is that when we evaluate make add, we have to bind X into the environment for this closure that we return here. So we're returning a function here, but X has to be instantiated in that function. So that add 1 and add 2 gives 2 different functions. Okay, so we call that a closure. So the way to implement that, you can do that in a couple of different ways, but the way we're going to do it today is that we're going to just instantiate all the free variables, capture the free variables inside this body. So capture free bars. And so we're going to give it the environment. And then we're going to say we have a body, and then we're going to instantiate all the free mentions in here. So values, nothing changes for these guys. And then for the rest, let's do them one by one. So here we introduce a new binding, but we have to recursively. So let's do that. We have to recursively substitute free variables in the value, and then we also have to do it in the body. But in the body, we don't want to do it for ID because it's not a free variable anymore. So we'll just say remove from tree. Remove tree, is that the name of it? I said remove from tree, I never remember. Like that. Here, we're going to say, if it's a free variable, it's going to exist in the environment. If not, it's just the var as it is. right? So this is where we instantiate in the example in here. The X is going to be bound to a value in that environment when we evaluate it, and it's going to instantiate it to that value at that point. So basically, we are constructing a new lambda when we do this capture free variable thing, and that will instantiate all those free variables. All right, so what I'm going to do, because all of these guys are easy, I'm just going to do a shorthand like that. Just call it rec for recursion. That's helpful. Rec condition, rec then, rec else, like that. And p call fn map args rec p array map values rec, like that. And the same with this guy. Whoops. Map values rec. Okie dokie. So now we have this guy and something's wrong. What did I do wrong? A comma's wrong. So capture free variables, I have two bodies redefined. So let's call it let body. Okie dokie. So we have to put this guy in here. So we're going to construct a lambda where we have captured free variables in the body. And that's what we're going to return. All right. So let's see if that works. It gave us 3. Lo and behold, it works. So now we have implemented, I think, all of the language. Should we double check? In the interpreter, do we have anything that we didn't do? I think we did everything. And this is basically the lambda calculus. So this is how you can implement the lambda calculus as an interpreter. And I think
Asger, can I ask a question?
Sure.
Can you show the section where you implemented arithmetic operations and comparison and so on? Yeah. So my question is, why, for example, for negate, you call get pinned on args 0, but for example, for just plus, you, okay, probably I overlooked it. The same. Okay, maybe you already fixed it.
Obviously, now we construct this tree many times. Each time we evaluate it, so this interpreter is not super
sorry,
fast.
no questions. Yeah, okay, sorry.
So what you can do in cases like this is that we have something called only once. So let me, some of you may know that one, but let me just so this is the type of the tree. It's this guy, right? So what we'll do is that we'll say build in ops is ref none at first. And then we'll say only once on this guy. And then it'll call this thing and instantiate that global variable the first time we call this guy. And thus the type of built-in ops up here is going to be a ref to maybe of this guy. So it's like a singleton construct. Only once. It's a helpful little piece of machinery. And then we can do it like this. Whoops, what did I do wrong? It's not only once I should look up on, it's this guy. And it's what did I do wrong? Oh, it's we get the ops out of only once. That's what's wrong. It returns the thing we want to look up like that. All right. So just to clarify this only once thing, if we look at it up here, so it takes that a placeholder for the value and then a function to initialize it. And it's very simple. If you look at the implementation, it makes sense. So if it's none, we call the initialization and then update that pad and return the value. and all the other guys, we don't call the value once, more than once. So this helps optimize things a little bit. So we initialize this tree the first time we handle a build-in, otherwise we don't. All right. So any other questions? Pretty clear, I hope. Let me see, are there any in the chat? Doesn't look like it. Okay. So I hope that it was useful and that you enjoyed this one. See you again next time.
Yeah, well, Asger, wait.
Okay.
I see Daniil is writing in the chat.
Okay. I don't know how to get this thing to be big again. Oh, I should probably stop my sharing. Okay. Yeah. So he's writing something. I have one question. Okay, what's the question, Daniel? Why do we need another version of grammar? Why we have Gringo instead of Lingo? Is that your question? Or is it something else? Well, it's we don't need it. Lingo is great. It works fine. I think the key points here is that if you compare this grammar to the corresponding in Lingo you don't have these guys, which help make the precedence correct. And in Lingo, you don't have this guy, which makes associativity correct. So that's a benefit. The other benefit is that in Gringo, you don't have a binding of the semantic values. Instead, you have a stack semantics, and that means that the semantic actions are, you don't have to bind all the values. You just they just push things on the stack, and that has another benefit that the semantic actions are typed. So in Lingo, you have to use flow, the untyped flow value, to get the semantic actions to work. But in Gringo, they are strongly typed. So you will get type errors if you do it wrong. So I recommend you watch the previous stream where I also explained some of this. But thank you for the question. All right, anyone else? Doesn't look like it. So thank you very much and have a nice weekend, everybody. Bye-bye.
Thank you.
Yeah, bye.